An integer is a number that can be written without a fractional component. For example, 21, 4, 0, and minus 2048 are integers, while 9.75, 5.5, and square root 2 are not. The set of integers consists of 0, the natural numbers, also called whole numbers or counting numbers, and their additive inverses. This is often denoted by a boldface Z or blackboard bold standing for the German word Zahlen. Z is a subset of the sets of rational and real numbers and, like the natural numbers, is countably infinite. The integers form the smallest group and the smallest ring containing the natural numbers. In algebraic number theory, the integers are sometimes called rational integers to distinguish them from the more general algebraic integers. In fact, the integers are the algebraic integers that are also rational numbers. Algebraic properties. Like the natural numbers, Z is closed under the operations of addition and multiplication, that is, the sum and product of any two integers is an integer. However, with the inclusion of the negative natural numbers, and, importantly, 0, Z is also closed under subtraction. The integers form a unital ring which is the most basic one, in the following sense. For any unital ring, there is a unique ring homomorphism from the integers into this ring. This universal property, namely to be an initial object in the category of rings, characterizes the ring Z. Z is not closed under division, since the quotient of two integers need not be an integer. Although the natural numbers are closed under exponentiation, the integers are not. The following lists some of the basic properties of addition and multiplication for any integers a, b and c. In the language of abstract algebra, the first 5 properties listed above for addition say that Z under addition is an abelian group. As a group under addition, Z is a cyclic group, since every non-zero integer can be written as a finite sum 1 plus 1 plus 1 or plus. In fact, Z under addition is the only infinite cyclic group, in the sense that any infinite cyclic group is isomorphic to Z. The first 4 properties listed above for multiplication say that Z under multiplication is a commutative monoid. However, not every integer has a multiplicative inverse, e.g., there is no integer x such that 2x equals 1, because the left-hand side is even, while the right-hand side is odd. This means that Z under multiplication is not a group. All the rules from the above property table, except for the last, taken together say that Z together with addition and multiplication is a commutative ring with unity. It is the prototype of all objects of such algebraic structure. Only those equalities of expressions are true in Z for all values of variables, which are true in any unital commutative ring. Note that certain non-zero integers map to 0 in certain rings. At last, the property says that the commutative ring Z is an integral domain. In fact, Z provides the motivation for defining such a structure. The lack of multiplicative inverses, which is equivalent to the fact that Z is not closed under division, means that Z is not a field. The smallest field with the usual operations containing the integers is the field of rational numbers. The process of constructing the rationals from the integers can be mimicked to form the field of fractions of any integral domain. And starting from an algebraic number field, its ring of integers can be extracted, which includes Z as its subring. Moreover, Z is a principal ring. Although ordinary division is not defined on Z, the division with remainder is defined on them. It is called Euclidean division and possesses the following important property. That is, given two integers a and b with b 0, there exist unique integers q and r such that r equals q times b plus r and 0 are less than b, where b denotes the absolute value of b. the integer q is called the quotient and r is called the remainder of the division of a by b. The Euclidean algorithm for computing greatest common divisors works by a sequence of Euclidean divisions. Again, in the language of abstract algebra, the above says that Z is a Euclidean domain. This implies that Z is a principal ideal domain and any positive integer can be written as the products of primes in an essentially unique way. This is the fundamental theorem of arithmetic. Order theoretic properties. Z is a totally ordered set without upper or lower bound. The ordering of Z is given by -3 less than -2 less than -1 less than 0 less than 1 less than 2 less than 3 less than. An integer is positive if it is greater than 0 and negative if it is less than 0. 0 is defined as neither negative nor positive. The ordering of integers is compatible with the algebraic operations in the following way. If A less than B and C less than D, then A plus C less than B plus D. If A less than B and 0 less than C, then AC less than BC. It follows that Z together with the above ordering is an ordered ring. The integers are the only non-trivial totally ordered abelian group whose positive elements are well ordered. This is equivalent to the statement that any Noetherian valuation ring is either a field or a discrete valuation ring. Construction. In elementary school teaching, integers are often intuitively defined as the natural numbers, 0, and the negations of the natural numbers. However, this style of definition leads to many different cases and makes it tedious to prove that these operations obey the laws of arithmetic. Therefore, in modern set theoretic mathematics, a more abstract construction, which allows one to define the arithmetical operations without any case distinction, is often used instead. The integers can thus be formally constructed as the equivalence classes of ordered pairs of natural numbers. The intuition is that stands for the result of subtracting b from a. To confirm our expectation that 1 minus 2 and 4 minus 5 denote the same number, we define an equivalence relation tilde on these pairs with the following rule. Precisely when addition and multiplication of integers can be defined in terms of the equivalent operations on the natural numbers, denoting by the equivalence class having as a member 1 has. The negation of an integer is obtained by reversing the order of the pair. Hence, subtraction can be defined as the addition of the additive inverse. The standard ordering on the integers is given by IFF. It is easily verified that these definitions are independent of the choice of representatives of the equivalence classes. Every equivalence class has a unique member that is of the form or. The natural number n is identified with the class, and the class is denoted -n a second time since -0 equals 0. Thus, is denoted by if the natural numbers are identified with the corresponding integers. This convention creates no ambiguity. This notation recovers the familiar representation of the integers as -2, -1, 0, 1, 2. Some examples are computer science. An integer is often a primitive data type in computer languages. However, integer data types can only represent a subset of all integers, since practical computers are of finite capacity. Also, in the common 2's complement representation, the inherent definition of sign distinguishes between negative and non-negative rather than negative, positive, and 0. Fixed-length integer approximation data types have denoted int or integer in several programming languages. Variable length representations of integers, such as bignums, can store any integer that fits in the computer's memory. Cardinality. The cardinality of the set of integers is equal to 0. This is readily demonstrated by the construction of a bijection, that is, a function that is injective and surjective from z to n. If n equals 0, 1, 2, then consider the function. If n equals 1, 2, 3, then consider the function. If the domain is restricted to z, then each and every member of z has one and only one corresponding member of n, and by the definition of cardinal equality the two sets have equal cardinality.